from the University of Lyon, and he will talk about integration in finite terms and exponentially algebraic functions.
So thank you for the invitation and thank you for the introduction. So it's a pleasure to be here. So I'm going to talk about a project that we started around 2 years ago with Jonathan Kirby. We're still finishing writing at the paper, but about the problem of integration in finite terms from a model-theoretic perspective. And so the kind of questions we are interesting today is the following question that was asked by Liouville. Okay, so I'm first going to describe the naive form of the questions and then how to make it more precise. And the question is the primitive. Okay, so I'm going to write it like that. So this is just the sign for taking an antiderivative of eta. So it's the primitive of an algebraic function. So you give yourself an algebraic function, eta. Okay, and the question is the primitive expressible? Okay, using log sign, using algebraic signs, logarithmic signs, and exponential signs. Okay. And so, of course, what is not precise about these questions is what I mean by expressible. Okay, and so this is what we are going to change compared to the classical theory. And the first thing, so my plan is first to explain you the classical theory. So many of you must know the classical theory of the problem of integration in finite terms. I'm just going to, there's a whole bunch of mathematics on these questions. I'm just going to describe what is needed. And the second thing is, so what we change compared to the classical setting, and we are going to change what we mean by expressible here. And this is the concept of exponentially algebraic function. Okay, and this is how we get some kind of new problem compared to the problem that people were asking in the classical setting. Okay, and then I would like to explain you the model-theoretic setup that we use, because in itself I think it's an interesting object. And then, if I have time, I will talk about the solutions, so exponentially algebraic solution in case of linear equation, linear differential equation. So let me first recall what we know about the classical theory. And so the classical theory is based on a definition to make precise what it means expressible here. And so the definition is a definition that was given by Liouville. Okay, and the first thing is that we are going to work in a complex setting. Okay, so we start with an holomorphic function. So I'm taking a function of one variable, an holomorphic function of one variable defined on an open set U. Okay, the holomorphic function. And you want to define when this function can be expressible by algebraic signs, logarithm signs, and exponential signs. And what you will say is that, okay, we say that f is elementary. So the first thing we're allowed to do is to shrink the domain of definition of your function. So if after, if working on a domain V included in U, maybe not on the full open domain where the function is defined, it can be expressed, it can be constructed. Constructed. From the variable z, okay, using the following operations. Okay, so the first thing that you do is you add all the arithmetic operations. So if you take the sum of two functions that were elementary, the sum is still elementary. If you take the product, the division and everything, and I'm going to involve in complex numbers. Especially because this notion is studied also in computer algebra. Sometimes people don't involve complex numbers in the definition of an elementary function. Okay, to have a notion that works over Q bar. So in my situation, I'm always allowing arbitrary complex numbers in my function. I'm working over C. Okay. And the second thing is you allow to precomposition by X and branches of the complex logs.
The domain simply connected.
So you can you can assume that your V is simply connected. Okay. So I'm going to make a remark on that after. So it's just that this definition given by Liouville, it's for a holomorphic function, and so this is around 1833. And there's somehow a little bit improved version of this definition given by Ritt, where the functions are not holomorphic functions, but they are multi-valued functions. Okay, and then in that case, it's a little bit simpler to be about the branches of the complex log. But here, because you're allowed to shrink the domain, you can always assume that things are simply connected.
Do you allow to solve algebraic equations or not?
Here, an extracting root. Of algebraic equations.
So intuitively, one thinks that if there is such a thing on some small disk V, then although the functions are sometimes multi-valued, usually when you try to extend analytically, you have only isolated singularity, that's integer zero, so you can think intuitively you can somehow extend. So in particular, the following property should be that if it is elementary on some non-empty open set in U, then it is elementary on every other non-empty open set in U because of this intuition. So is it actually something I can prove rigorously or?
So you can prove that it's enough to get rid of a countable number of points where there's a problem. But an important example, if you want, is a function which is cosine of square root of z. Okay, because this is an entire function, and to witness that it's elementary, you need to get rid of the zero, where this is where to introduce this. Okay, and this is so that's why you sometimes need to shrink the domain and to throw away a couple of points.
Okay, so in other words, if you throw away a countable discrete or not discrete?
Yes, countable discrete.
Countable discrete, yes. Then you can cover this by small disk for which it is elementary in this sense.
Yes. Okay, but so as explained, we are going to change this definition. Okay, so this is not the definition we are going to work with, but this is the classical definition of Liouville. And so as pointed out, there's several things to be careful about in this definition. And if you look in the modern version of this definition, which is given in Ritt in 1948, okay, it takes 5 or 6 pages to make this recursive definition very precise. Okay, so there is a little bit of precision to give, but the important part is that you get a well-defined notion of what it means to be expressible using algebraic signs, log signs, and exponential signs. So 2 problems that you will consider, okay, which are problems of integration in finite terms. So I will give you some concrete examples. So you fix a rational function of 2 variables and a polynomial. Here. Okay, and the first question is the algebraic problem. Okay, which is essentially the one that I formulated before. It's for algebraic function. So, for example, is this integral, this antiderivative, elementary? Okay, so this is a typical question that Liouville is asking. You take a rational function of 2 variables, you allow a square root. Can you compute this primitive? Is it expressible? Is it an elementary function?
But of course, you can take the variable square root z as another variable, and then you reduce to the calculus information on how to integrate.
Mm-hmm. So
then you know what to do.
So it's not always the case that it's elementary, but in many cases, so we'll see how to reduce it. But so one of the important parts about Liouville's work is also to look at the transcendent problem. Okay, which looks very similar. So is the integral, but this time instead of putting a square root, you put an exponential, for example. You could take a log. Okay. And actually, what we know now from the point of view of computability theory is that this second problem, of course the restricted one here that I formulated, is actually simpler to solve than this one. Transcendental problem. So what I mean is that you don't try to integrate an algebraic function, you try to integrate a transcendental function. Okay? But you can see that here I gave you only two particular examples, but this problem is easier to solve than this one. If you ask a computer, Mathematica, an explicit form of R and an explicit G, and you ask it, is it elementary? Okay? It will converge, so there are algorithms for doing that, and it works much better on this example than this example. So actually, the algebraic case is not really simpler than the transcendent problem. Okay, and we will see that the theorems, they are common in the two setups.
And you integrate on what kind of?
So it's an antiderivative, right? So I'm looking for a function that satisfies y prime is equal to this on some domain. Okay, so this is defined, I'm taking a simply connected domain where this defines a function, and I'm asking, can I shrink my domain so that the function becomes elementary?
I'm a bit confused. So if you have a rational function of z and square root of z, in particular it's a rational function of square root of z,
yes.
And this is twice square root of z, this square root of z. So you reduce an integer as a variable square root of z. Then you have a rational function, it has partial fraction, expansion, and so on. And we know how to integrate it. So
yes.
you only get elementary guys, and so you don't get anything.
Yes.
Okay,
so I forgot the G of C.
Okay.
It's not like otherwise. So, yeah. Thank you. Yes.
If G is known,
Sure.
G is complicated enough to.
So that's what I'm going to say now, okay? And it's is that there's an easy observation, that is the one that you just made, and all Liouville also did. Okay, is that if the curve y squared is equal to g of z, okay, is as g is 0. Then this integral is always elementary. And so the idea is the following. I'll just give an explanation. So let me take a particular case to give the explanation. So the example I want to give is just to take g of z is equal to y minus z squared. And you see that if you take g of z is equal to 1 minus g squared, this becomes this equation of a circle, a complex circle, of a circle. Okay? So in that case, the curve is rational, and you have a well-known parametrization. So you consider, so step one, you consider the rational parametrization. Okay, so what you do is, so it's well known in the case of the circle, you have the map from P1 of C to C, in this case C squared, so the curve is curve C. Okay, and it's given by 2s, you associate 2s minus 1 divided by s squared plus 1, and x squared minus 1 divided by x squared plus 1. Okay, and in the other direction, it's given by 2yz. Okay. You associate y divided by z divided by 1 minus 1. Okay? And so what you do is that you have your one form r of z square root of z of square root of g of z dz. Okay, which lives on this on this curve. You pull it back. Right, so you have this form omega here on C. Okay, you consider the pullback phi étoile of omega.
No, it's not exactly the inverse. You have to change the slide by linear.
So you consider phi étoile of omega. Okay, so you pull back the form on P1 of C. You get the form of the form H of S times ds. Okay, where H is a rational function, and then you integrate H of S ds. Okay, so using partial fraction decomposition, you integrate this function as being a rational function plus the sum for alpha poles. So H is not F. Notation, the pole of f of z of the residue of f at the poles times the log of the s minus alpha. Okay, this is everything is dependent on this. Okay, so you pull back your form, you get a rational one form of P1, you integrate this rational one form, and you see that the shape is the sum and the sum of log, and then you replace S by Z minus 1, Z divided by Y minus 1.
No, it's not exactly the formula. It's not Z over Y minus 1, you can easily see, but something close to it.
So I made the computation before, so maybe I made a mistake in the computation, but I think this is, so. Okay, so the formula should be, maybe the formula is wrong, but I mean, I think I made the computation before, I think, but
maybe the formula that you give for the
you're right.
The solution is not
2S.
correct.
Okay. Yeah. So this is the parametrization with tangent theta over 2, and you know it's the usual parametrization of the circle that also allows you to find the Pythagorean triples. Okay, it's a very standard object. And so at the end, what you will get, let's write it here. At the end, what you get is that the integral of R of z dz is of the following form. It's f0 over z divided by square root of q of z minus 1 plus a sum, finite sum of complex numbers time logs of the same thing of z divided by square root of z minus 1 minus 7. Okay. So this is something that was very classical in Liouville time and that we now teach in course of calculus on how to compute it when the curve here has genius 0. Okay? But when the curve, when you look at more complicated, so the curve has genius 0, if there's no singular points, the g of z must have degree 1 or degree 2. Okay, but as long as g of z has degree 3 and 4, the genius is greater than 0. Okay, and this method doesn't work. Okay, it doesn't mean that the integral is never elementary. Sometimes this method doesn't work for integrating, and the integral is still elementary. Okay, so the point of the Liouville theorem is to show that the shape of the formula remains the same, and it even remains the same in the transcendental case. So let me state it now. So it's Liouville, which says the following thing. So you start with an elementary function, let f of z be an elementary function. Okay, and assume that you can integrate it, and assume that the primitive is elementary. Okay. So what Liouville theorem will tell you is that the primitive has exactly this form here. Then the integral on the primitive of f of z dz is of the following form. It's a rational function plus a sum, a weighted sum of logs. So exactly the same format here, a rational function plus a weighted form of logs. And what you should put inside here, you should put f, you put z, f of z. Okay, so this is, you see that this is exactly what you have here. And to deal with the transcendental case, you just need to add the derivative. Okay, so if you can write it, it can be written as a rational function on the data and its derivatives. And same thing here. So if you go back to the two examples I gave you, okay, you get that f prime of z. Okay, so in the two examples I gave you, so f prime of z, let me not use the atmospheric notation, is in the function field generated by z and f of z. Okay, for f of z, which is of this form, or f of z, which is of this form. So that's why these are the two canonical examples. I mean, one reason why these two examples are easier than the general case is that in these two examples you can compute the derivative of f, and you can rewrite it in terms of f and f of z and f of z, and therefore all the terms that are the higher derivative, they vanishes. Okay, and so in these two cases, it's possible for this reason to do computation that helps. Okay, and so Liouville reaches the following term of equations. You have to solve. Is it possible so that you have an equation, let's say like that, is equal to R0 of z plus the sum CR R0 of z square root of g of z plus the sum of log. Okay, so if you assume that your function is elementary, then it can be written in these forms. Okay, and now you're going, so the indeterminates are here, the indeterminates are R0 and the Ri. The function g of z is given, the function r is given. Okay, and here, so Liouville uses just a computation of residues. Uses, and so take the derivative. And compare residues.
Is it important it is the square root of g of z? If it is another root, it's also wrong?
No, so just for practical computations, the computations are much harder, but the theorem is valid for any elementary function. So any algebraic function.
No, but the remark that it's enough to, you don't need the derivatives.
So for the algebraic case, it's always the case. Okay, for this case, you can take any algebraic function, the derivative is always. So for this remark, no. This is true for any algebraic. Anytime f of z is an algebraic function, you will have that f prime of z is equal to here. In the transcendental case, now it's a particular form.
Ah, okay.
In the algebraic case, this is always true. Okay, so so this theorem, when it's formulated for algebraic function, you get rid of the derivatives.
Okay, it's clear.
Okay. Okay, so this is what. And so some examples that Liouville is able to study using this technique. Okay, so there are first some algebraic examples, and the main algebraic example he studies are integral of this form, so he studies other kinds of elliptic integrals. But the one we will use is that this one is not elementary. So when the elliptic curve doesn't degenerate, and so when 4a cubed plus 27b squared is not 0. Okay, when the elliptic curve doesn't degenerate, this is not elementary. Okay, and the second example, so he studies, for example, e to the power minus z squared dz. Okay, so because this one appears in statistics, so you know how to compute the integrals from minus infinity to infinity. Okay, and here the point is that you cannot compute the full antiderivative. Okay, he also compute these ones, so it's a little bit different form. But you see these functions appear in the prime number theorem, the integral is important, okay, and these functions is also not elementary. And the last one that he computes is this one, which is called the Fresnel integral, okay, and which appears in optics. This one in statistics, this one in number theory.
And the second one, shouldn't it be divided by L and Z? Because right now it is elementary.
This one?
Yes.
Okay.
Now you're just at L and Z.
Sure. Okay. So let's put one that looks like integrable. Okay. Okay. And so you see that he actually computes much more transcendental ones. Then he has one family of algebraic ones. So these ones are important for him because they appear in the solution of the pendulum. I'll try to explain that a little bit later. But actually, it's much easier to make computation with transcendental functions.
So the logarithmic integral, as far as I remember, is something like the integral of dz over lambda, without the z. The one in the prime number theorem is like the what? Yeah, so it's without the z.
Nous on pose u égale z2, ça devient du du sur revenu.
Let's get rid of this one. So you can put integral of I don't know. You can put yeah. Okay. So let's just get two examples. He studies several examples. Okay, but my point is that this is actually not harder from computation perspective, and so this was very old mathematics. And so what is happening nowadays is a problem of integration in finite terms. So a very important theorem that happened in the 1970s. It's called the Risch algorithm. So as you can see, Liouville studies the problems that are important in his own time. These functions, they appear in other people's work, and he wants to know if they are elementary or not. Okay? But the point of Risch is to show that the whole problem is decidable. Okay? And so the thing is that problems A, let me formulate it like that, and problems B, problems A and B, are decidable. Okay, and so more generally, so this I've formulated here A and T. Okay, and more generally, so formulated in the correct syntax. Okay, the full problem of integration in finite terms, full problem of integration in finite terms. Is decided. And as I said, actually, if you ask a computer, so this fact launched a big area of mathematics, which is symbolic computations, where people do both differential algebra and computer algebra, which is to design actual algorithm to solve this problem. And what I'm saying is that these algorithms, they are more efficient when you don't take in algebraic functions, but you take transcendental functions that satisfy simple differential equation than in the algebraic case. Okay, so the algebraic case is not at all the simpler case, except the case of elliptic functions that have a very elliptic integrals that have a very nice structure. Okay, so this is about the classical problem. Check out. Okay, how much time I have. So now I'm going to explain what we change in the classical problem to obtain new results. Okay, it's the concept of exponentially algebraic function. Okay, and what we are going to change is what it means to be definable by signs of x, cos, and log. And so the setup is the following. And so we are just going to consider, instead of expressible, we'd like to say as model theory is definable. Okay? And so we want to find a structure such that definability in this structure is going to correspond to expressibility in terms of x, log, and signs. And so we are going to consider the following structure, consider the structure. So that Van den Ries calls the structures of restricted elementary functions. And it's just you take the semi-algebraic geometry on R, okay, and you expand it by a bounded version of the complex X. So you just fix this structure, okay, you have the R and so all semi-algebraic geometry, and you add one symbol for the exponential function, okay, it's a partial function, and you extend it on the bounded domain.
Yeah, it's independent of the ball.
It's independent of the ball, yeah, sure. So you can take balls arbitrarily. Okay, and so what is behind the fact that the notion that I'm going to define is well behaved is the theorem of Van den Ries. Okay, when he introduced this structure, also the title of the paper is on the elementary theory of restricted elementary functions. Okay, and you see that the word elementary is used first in the sense of logic, and then in the sense of Liouville, on the elementary theory of restricted elementary functions. That's the name of the paper, and so it proves that the structure is hominimal and model complete. Okay, and as a consequence of this, the notion of definability in the structure will be very well behaved. So this is the definition 2.
So model complete has to do with elimination of multipliers?
So it's formula, so here it's strongly model complete, so but every formula here is equivalent to an existential formula. So the projection of a quantifier-free formula.
Okay.
So the definition is that let f be an holomorphic function, so you start with your holomorphic function. Okay, I'm taking it one variable again, but here there's absolutely no reason to do that. And you say that f is exponentially algebraic, so I will explain the terminology later on. Okay, if the germ of f at some point of its domain is definable in the structure of restricted elementary function.
Does it follow that any other germ is in the connected cases also?
So it's the same problems than before, right? You can have to throw up a little bit of point. It is unknown if this is equivalent to say that the function f is definable. So the problem is that u is not bounded here. Okay, I'm not assuming that u is bounded. But so it's not true, it's not known if it's equivalent to say that the germ at every point is definable. This we don't know. If it's equivalent, this definition, to say that at every point, the germ is definable in RRE. Maybe Tamara knows that, but yeah.
Okay, so the answer here is that it is not known, although maybe it's true.
Yes. So, but this is the weakest notion. So that gives you the strongest notion of non-integrability, except of taking at all points. So the first thing, which is not very hard to see, is that every function that is elementary, in the sense of Liouville, is exponentially algebraic. Okay, so if you give yourself, so how do you define? So every function that is elementary in the sense of Liouville is definable, is exponentially algebraic in this sense. That's why it's called the function of the structure of restricted elementary functions. Okay, so the important example is an example that is exponentially algebraic, but is not elementary. So this is the example I'm going to describe now. And the example is called the Lambert function. So there are many examples, but I'm going to give you the simplest example in my world. It's called the Lambert function. And actually, to find it, you don't need to go much further. You just have to go at Liouville, but his work that is just after, in 1837. The theorem before is 1835, and actually he studies this function in a paper just after. Okay, and so he's aware of, somehow of the existence of two definitions, although he cannot phrase it like that. And so the function is like that. So I'm going to give it as a power series at 0. So it's the sum of minus n to the power n divided by n factorial times z to the power n. Okay. So defined like that. So this is you can see. So the radius of convergence is 1 over e. So if I make a drawing, so this function is exponentially algebraic and not elementary. Okay, so how to see that it's exponentially algebraic? So the fact that it's not elementary, that's what Liouville proves. Okay, and what remains to be seen, so Liouville proves that it's not an elementary function, and the problem is to show that it's exponentially algebraic. Okay, so what I'm going to use is that actually, so y, so the important equation is that this function, so why is it important? Because it satisfies the following functional equation, is that this function, if you plug in it here, you will get z. Okay, so if you take the function z times e to the power z, okay, and you evaluate at w, you will get the identity function. Okay, so if I make a drawing, you have this. So you have the plane with coordinate z, you have the plane with coordinate w, okay, and the function that goes from one to the other, I'm going to take it like this function, so the function is here.
What is 0 to the 0? In the definition?
I don't know.
You start at 1?
So what do you mean 0 to the 0, e to the power 0?
No, because the formula is from 0 to infinity. So then there is 0 to the 0. I'm not sure what it is.
So let's take
n. 1 is okay.
Yeah, so let's take n equals 1. So w of 0 is equal to 0.
Okay, then
So the first position is
w0 equals 0 would not satisfy the equation. Oh yes.
Yes, okay.
Okay, then this is
So if you take this function z e to the power z and you compute the derivative has a problem at -1. -1 is the point where the derivative vanishes, so the derivative vanishes of this function vanishes exactly at this point. Okay? The image of this point is -1 over e. Okay? -1 over e is exactly the radius of convergence of this power series. Okay, so this power series goes from this, it sends this circle here, on this circle here. Okay? And this is, so this function z e to the power z, it's a biholomorphism between this disk, and the Lambert function is just the inverse of this biholomorphism. Okay, so if I write it well, you see that, so take phi. So this is u, and this is v. So take phi from u to v to be the function which to z associate e to the power z. Okay, so this is an isomorphism. Okay, and so phi is definable in R, Re. Okay, this is because this is an elementary function, and this is equivalent to say that the graph of phi is definable, and so this is equivalent to say that phi minus 1 is definable in
it cannot be biolomorphic. biomorphism from precisely under this, because -1 goes to something 1 over E, but 1 will go to E, which is big. I mean, it's not in the same.
So this function is radius of convergence is 1 over E.
Yes.
Okay, so it defines a function which goes in the other direction. So at least at the germ, so let's just look at the germ at 0.
Okay.
Okay, the germ at 0 of this one is invertible. So on some open set it will be invertible, and on some open set, and then this equation holds on some open set. But then, because it holds on some open set and they are analytic functions, and it will hold everywhere where you can extend them, so it will end on the locus here. Okay? So what I'm saying is that this is what you're using, so you see that this class of functions that are exponentially algebraic, it has this property that if you take a function that is exponentially algebraic and the biomorphism, its inverse function is. Okay, so this function appears in the solution of several problems of mathematics. I'm not going to give you a complete list because we don't have time, but this is an important function in mathematics. Okay, but I want to use it to compare the two classes. So compare comparison between the class of elementary function and the class of exponentially algebraic function. And so what is the important problem? So what are the problems of the class of elementary function? That the class of elementary function, so I'm going to give you an example, is not stable under the implicit function theorem. Okay, and it's precisely for this reason that Liouville started to study the Lambert function. Okay, he wanted some concrete example where you can show that this class is not stable under the implicit function theorem, and so the example is that you just take the previous example. So you take the function of two variables this time, which is z e to the power z minus w. Okay, and so the implicit system which is f of zw is equal to 0 and df over dw of zw is not equal to 0, okay, has no solution, has no elementary solution. Okay, and on the other hand, the class I've defined of exponentially algebraic function is stable under the implicit function theorem. And why? Because the structure is hominimum. So we are using a theorem to get it, right? It's not like you take definability in any structure, it will be true. Okay, we are using the good property of hominimum structures to get that this class is stable under the implicit function theorem. And actually, so I'm not going to state it exactly because it's a little bit annoying to state, but the theorem of Wilkie,
Why we need the second equation? Because this derivative is -1, so it's not 0. I don't understand what's the role of the second equation.
So it's to get an implicit. So when you want to solve an implicit system, you have to ask that the derivative doesn't vanish. Okay. So the fact that this system,
this implicit system has a solution, namely z e to the z itself. You're confusing the variables. So
you're right. So it's this one. That's what you say? So there are two variables, you have to pick the right one. So the solution, so you want to solve in W, you want to solve Z in terms of W. So you're right, this is this system. So yeah. Yeah. And so actually, so the theorem of Wilkie says that essentially, and this is in the essentially that I don't want to be too precise, the class Cx is the closure of the class Cl under the implicit function theorem. Okay, so if you don't want to think about definability, okay, you can try to get back to Liouville definition. You add one more operation, which is solving implicit functions, okay, and you will get a class of function which essentially plays the same role as Cx. Okay, so this is the way of thinking about these two classes of function. This one is obtained from this one by closing under the implicit function theorem. And so the second example I want to describe, and that is for me a real motivation to look to exponentially algebraic function, is that the class Cl, so when you work with elementary function, okay, the class of elementary function is not preserved, so the notion of elementary function is not preserved under change of variables, under elementary changes of variables. Okay, so if I take back my example of before, so you have your open domain here, which is sent to this model disk. Okay, and what happens here is that if you look at the function w of, so here this is the coordinate w as r, so it's always z, and here the coordinate are w. Okay. So now, if you compose, so if you take a function, an holomorphic function here, f, okay, you can compose it here and get a function here. Okay, so the point is that if you start with an elementary function here, okay, because phi is elementary, this will always be elementary. Okay, so if this is elementary, then this is elementary. Okay, but the converse doesn't hold. If you take the function w of w here, okay, and you apply it z e to the power z, okay, you will get the function z. Okay, so
if this is an elementary change of variables, because it depends on how you define elementary change of variables.
So an elementary change of variables, I'm just saying here is that the class of elementary functions is not stable under compositional inverse. So here what happens is that f is elementary, but f minus 1 is not elementary. Okay? And this is why you create new functions when you do like that. Okay? And when you work with exponentially algebraic function, this doesn't happen. If something is exponentially algebraic, this is what we said here, phi minus 1 is exponentially algebraic. Okay, and so you see when you want to work with change of coordinates and everything, this system, this class of functions is much more, is more natural to work geometrically in this class of function than in this class of function. But the class of elementary function has still a very nice property, is that the class of elementary function has strong decidability properties. Okay, so you have Liouville theorem. This is Liouville theorem applies here and not here, and you have Rich algorithm that applies here and not here. Okay, so our main theorem. Okay, it says that in Liouville theorem, you can replace elementary function by exponentially algebraic function. There's another result of this type. So Okay, so let me just give you an example. So how long do I have? So I have until...
We have more than 20 minutes,
Yes.
more than half an hour.
Okay. So I just want to give this example because I like it, although it's not very new things, but let me give you this example. Is how you can phrase Liouville theorem on elliptic integrals in this setup. Liouville theorem. On elliptic integrals. And so I want to use these kind of things that I can do change of coordinates to phrase a little differently the theorem of Liouville. And so what I'm starting with is with a pendulum. So you start with a circle, okay? So you have the center of the circle, and you have a particle that is moving under gravitation. So the coordinate as x of t and y of t. Okay, so it's a pendulum, it's a simple pendulum, so you have one particle that is moving on this circle back and forth like that, or if you give it enough energy, it will turn infinitely many times like that. Okay. So this is the equation, so consider the equation to consider. It's the equation of a pendulum. And so, if you write it usually in physics, it's written as an equation on the theta. It's written as an equation as theta double prime is equal to sine theta. Okay, and in this form, it's not an algebraic differential equation, and I don't like an algebraic differential equation. Okay, and so the goal is to make it algebraic, but it's so written in the coordinates for the position x of z, y of z, x of t, y of t. Okay, let's write it as a coordinate. Then it is an algebraic differential equation. Or the solution is given by an algebraic differential equation. Okay, it's just the Hamiltonian formalism gives you immediately something with on the tangent space of the circle. Okay, and this algebraic equation has a first integral okay, which is given by the conservation of energy. Okay, so here if you look at the energy of a particle, it will be 1/2 of the, so this is the kinetic energy. Okay, let's take m is equal to 1. Okay, and then you add the potential energy, so because you have the gravity acting like that, the kinetic energy is +1. Okay, so now let's make the computation, and so using this information, so how to compute it? Okay, and we are going to compute it using just basically differential algebra. Okay, so let me just choose the right normalization so that my computation is not too messy. And so the normalization that I'm going to take, okay, that my circle is going to be given by x squared plus y squared plus y is equal to 0. Okay, I'm just taking for the computation to be easier. And the energy, I'm going to take it to be 1/2 of x prime squared, so 4 x prime squared plus y prime squared, okay, plus y is equal to h. Okay, so I've just multiplied here by 8 to make my life easier, and here I've changed the circle from the unit circle to another version to get a computation that is a little bit simpler. So you see you have two equations, so now you take the derivative of one.
Oui. Parler de moins y.
I have minus, I think.
Non, non, la deuxième ligne.
No. Here?
Parce que tu as multiplié par un.
Yeah, I'm just changing the h. Okay, that's why I'm saying I'm choosing. So here I draw like this. So I'm just so if you want, you can add. You have constants here and constant here, but I'm just getting rid because it's just the convention to make the computation easy. And so now what I'm getting is that so x dot. So I'm taking the derivative of this. I'm getting 2x dot plus 2y dot minus y dot, y minus 1 y dot is equal to this. Okay. And now what I'm going to do is just to eliminate x and x prime for this equation. You see I can write it as 2y minus 1 square, okay, times 1 derivative of y. So I'm using this expression and it's given by 4. So this is 4x squared x dot squared. And now I'm using this to replace x squared. Okay, so this will be 4. So now if I replace x squared, I will have y minus 1. So minus y minus 1. Okay, and here I'm using the 4. That's why I cheated with the 4. To be able to use this 4 to express 4x prime squared here. And so if you do that, you will get this, so minus this times h minus y minus y dot squared. Okay.
Minus 4 y dot squared.
Minus 4 y squared. Okay. Okay, and now you look at them, so you get y minus 1, y minus h. Okay, and so this is this term here, and then there's terms in y prime which stays plus 4y minus 1, y prime squared. Okay. But now you see that this y dot square, you can eliminate it with this y dot square here, and you get 2y minus 1 square minus 4y square plus 4y, so you get 1. So what you get? The equation. So the equation of this pendulum, but written as an algebraic equation, is this equation. It's y dot square is equal to y minus 1, y minus h. Okay. And so here you recognize an elliptic curve. Okay, this is the curve y squared is equal to z squared is equal to y minus 1, y minus h. Okay, and so this function, it's really the local analytic inverse is given by the elliptic integral. And so Liouville theorem up to a change of coordinates that we are allowed to do because we are having these properties up to a change of coordinate, what Liouville theorem tells you is that this equation here is not locally definable in the solution, the complex solution of the pendulum. Are not exponentially algebraic unless h is equal to 0 or h is equal to 1. Okay? And what are the solutions for h is equal to 1? The solution for h is equal to 1, they are the solutions that leave from the unstable equilibrium and that goes back to it infinite many times. It's just the level of energy where you have enough energy to go all the way until the unstable thing, but infinitely slowly. And for these solutions, there are well-known formulas showing that they are elementary functions. You know, in the case where h is equal to 1, these degenerate into a curve of genus 1 where you can compute the integral. And so the only solutions, the complex solutions of the pendulum that are elementary are this function that goes infinitely slowly. Okay, okay, so this is just how in this setup we can reformulate in a more geometric way same theorem of Liouville about the elliptic integral. Okay, so this is why this setup is nice, and we are looking for overcomputation of this kind, okay, that we can do in this setup. about other kinds of problems of mechanics where these kind of functions play a role. Okay. So this was about the main result, and now I want to explain about the model-theoretic setup that we are using to prove this result. Okay, and first we are going to, so I'm going to give several ingredients, and the first one, so the first thing we are using, and this is a differential algebra. Okay, and there are several proofs of Liouville theorem. Okay, the one we are relying on is the proof of Rosenlicht. Okay, and the advantage of this proof is that it's purely a differential proof. Okay, so you can forget that your things are functions and just remember them as elements of a differentially closed field. So, for the rest of the talk, okay, we fix U, a model of the theory of differentially closed fields. So I'm writing 1, 0, but I will stop using 0 soon because we only do characteristic 0 anyway. Okay, so this is, you take a model of the theory differentially saturated, so which is saturated, okay, and this field of functions is equal to 0. Okay, so this is always fixed, and we always work over a fixed set of parameters, so this is fixed, and we work, K, always denote the field, the algebraic closure of the field of rational function. So we can work over a set of parameters, but the situation is a little bit trickier. So I'm going to phrase everything around these things. Okay. And so what we can say is that so the first thing is that we can analyze. We know a lot of things about types in differentially closed fields. So the notation. Okay. I'm going to denote P in SD of K, to mean that P is a type, a differential type in the sense of DCF0 with coefficient in K. Okay, and for those who don't, not using the language of model theory, this is just a set of prime differential ideals, okay, in this object. Okay. And so, a key notion of differential algebra is the notion of internality to the constant.
Is in one variable or can it be more variables?
So here, for a moment, I'm allowing several variables, but at the end of the day, we want to study functions. So the problem of Liouville is really about types of one variable, and we will get a good description, essentially for types of one variable. But for the moment, when I'm not putting anything here, I'm not fixing the number of variables. Yeah, but you're right. If I want to write here, so let's stick from one variable. This formulation here only works for one variable. So we say that a type P is internal to the constant. Okay, so it's essentially, so you want this condition to mean it's a generalization of satisfying a linear equation. Okay, and when you say satisfying a linear equation, is that you can find a fundamental system of solution. So if you can find A1 again, realizing P, okay, such that, so this would be a fundamental system of solution. So such that any other solution, any Y, realization of P satisfies that Y is in the algebraic closure of C, all the constants, A1, AN, and K. Okay, so if you can write, you can find finitely many solutions of your type, such that any other solution can be written as an algebraic combination of this particular solution and constants over the field of parameter you work with. Okay, and under these assumptions, okay, you can define, so under this assumption, okay, if you look at the group of, so I'm going to write it like that, the group of automorphism of, you look at the group of automorphism of your bit structure, which fits C everywhere, okay, which is fixed point by point, okay, and under this assumption, so as always, it acts on the set of realizations of P, okay, this is automorphism of your model, okay, so they will preserve the types, so they act on the space of types, and under this assumption, so if P is internal to the constant, P internal to the constant, okay, then this action, so image, then things, the image of this group. So this group is not a nice group, but the image in the set of permutation of U, okay, is denoted out. So I'm putting a P, okay, out P of C, okay, and the action of out P of C on P, okay, is isomorphic to the action of an algebraic group on an algebraic variety. Okay, so this is G of C, X of C, okay, where G is an algebraic group.
So, Rémi, but what is curly X? So it's curly C, I mean.
Curly C is the constant, so okay, yeah. So curly C is the set of X in U such that delta of X is equal to 0.
But you didn't say that it was I know it was.
Oh yeah, you're right. Okay, so curly C is small c. Okay. So you're right. With the note, yeah, I should have been more precise. Yeah. So curly C is.
Si je peux me permettre, c'est être interne, c'est dans la culture définissable.
C'est la culture définissable. Thank you. Merci. So it's just that, so for types in DCF0, you can have the same concept as for linear equations to have systems of independentialization, and then you can define a Galois group of your type. But of course, it doesn't work for all groups. It works only if your type is internal to the constant. Okay, it doesn't work.
Your curly C is not C because your A1AN is in a larger field.
Yes, that's why.
C is not C.
So, it depends on. So,
DCL, c'est le corps différentiel algébrique par C.
Yeah, but you can find this A1AN in U. Okay, you can find them in the prime model.
But they don't realize P.
Yes, they do realize P, but they don't realize P to the power n. Okay, so let's assume that P is weakly orthogonal to the constant.
Oh, because you're overlooking K. Sorry. Yes. Okay. No, sorry.
Okay, I just wanted to do something too quick, and then but it's just I want to give you. So the point is the following: is to differentiate the following functions. So we have make a table. So we try to understand. So we have a list of functions. Okay, and for each function, I'm associated its type in the sense of DCF0. So the first one I can take is sine of z. Okay. The second one I'm going to take is the elliptic integral. Okay, the third one I'm going to take is this e to the power minus d squared dz. Okay. The third one I'm going to take is the equation of the pendulum. And the the last one is the Lambert function. Okay. And so you try to get to list what you know about them in DCF0 and try to predict if they are elementary or not. Okay. And so these two functions, so the function sine of z, and so this type and the type of these functions, they are both strongly minimal. So first question you ask is, what is the dimension of your problem? That is the rank or dimension. Okay, so these two problems, they have rank 1. This type here, okay, it has rank 2. This type here has rank 1, so these two last times are also strongly minimal. The second question is, which one are internal to the constant? Minimal analysis. Okay. So this type, these two here are internal to the constant. So this one is internal to the constant, this one is internal to the constant, this one too, only this one is not. Okay, so this one is internal to the constant. Okay, this one's 2, this one's 2, and this one is not. Okay, and the last one is what is, rank analysis. And Galois group. And so the Galois group of the first one, of the sine function, is the multiplicative group. The Galois group of this one is the additive group. The Galois group of this one is the affine group. The Galois group of this one is an elliptic curve. And this one, it's not internal, so it's not applicable.
Is it analyzable?
No, it's strongly minimal and geometrically. It's completely disintegrated.
Completely disintegrated.
Yeah. Okay, and now you know the answer that you want to get. So what is the answer? Okay, is that so? This one is clearly even an elementary function in the sense of Liouville. It's exponentially algebraic. This one is not. This one is not. This one is not, and this one is. Okay, and so we were looking at this kind of table for a long time to try to look at what can be true. Okay, and so you can see that these two examples, they look very similar. Okay, so they are both same rank, both internal to the constant. Okay, and here the Galois group is multiplicative and here it's additive, but if I change the function, the trigonometric function by its inverse, then this group will become the additive group. So you cannot say anything substantial. Okay? So here, okay, when the Galois group is not a linear algebraic group, okay, then it implies that the function cannot be elementary. And this is actually how in our setup we get the proof that this is not an elementary function. It's first by studying the pendulum. So this is not the square here. First by studying the pendulum, using that the group here is the elliptic curve, okay, and this is an obstruction to exponential algebraicity, and then come back to study this one. And this one is the affine group, also it's not possible, but you see that when the thing is not, so it has the worst properties, it's not internal to the constant, you cannot even apply your Galois theory here, it doesn't guarantee that your function is bad. I mean, that's not exponentially algebraic. Okay, so the idea that we got after quite some time is to look at a reduct. Second ingredient that we are using. Okay. And I'm not going to be very precise, so how long, I don't have a lot of time, so let me not be that precise about that. But the idea is what? Is to work in a reduct of DCF, where this function, we are going to forget the semi-minimal analysis of these three functions while keeping these ones. Okay, so we want a reduct of DCF, so just give a definition. So let F be a collection of empty set definable subset of u to the power n. Okay, so this is a differentially closed field. We just fix a collection of any kind of collection of functions and consider what we are going to write, consider the following structure. You see, it's very similar to what we were doing before. We take U like a differentially closed field with the algebraic structure, but we forget the derivation, and instead we only remember F. Okay. So we consider this here as a reduct, of this. Okay, so we just remember some information. We forget over information. And so the global picture, the kind of global picture about reduct, of a reduct was done by Vahagan Aslanian, just making sure I'm writing it well. Okay, and we study what kind of objects can appear here. So just if you take F inside the collection of algebraic subsets, okay, what do you get as a reduct? Okay, so if the only sets you're allowed here are not definable using the derivation, but just using algebra, then you get ACF. Okay. The product is be interpretable. Okay, and so the result is not very interesting in that case. And so another case we can take is to take F to be the field of constants, C. I was asked about. Okay, so if you take F to be the field of constants, you get the pair of algebraically closed fields. And so what do we take in our setup? We want to take a F, okay, that corresponds to taking the exponential in the other thing, and so we are going to take gamma, x equal to gamma, where gamma is given by delta of y divided by y is equal to delta of. Okay. And so these three reducts, it's a non-trivial fact that, for example, it's not the full differentially closed field itself, it's not interpretable with the whole thing. Okay, and the local picture, so what we are going to look at is the local picture. Is that when you give such a reduct, so of course, there's no reason for an arbitrary reduct to behave well. This is a way to general definition. So how do we get to something that is a little bit nicer? Is to look at the loop. So we look, so given a reduct TCF0 RF, we obtain a continuous surjective map that we denote the reduct map from the space of type of DCF0 to the space of type in the sense of this reduct. Okay, and so this is surjective, and to understand the reduct is to understand how this map is working. So for example, what does it mean that the reduct is being interpretable with DCF? It means that this map here is an isomorphism. Okay, so if you want to understand how the reduct is for getting information, you should think about how the points are getting here, and the definition we are getting is the following. And we say that the type P in SD of K in SD of K has a faithful reduction, if this map where P implies P. Okay, in this case. Okay, so what does that mean, that P has a faithful reduction? It means that if you take the type P and you look at the image here, it's the only pre-image. Okay, so the reduct knows everything about the type. Okay, and I don't see any reason to believe that in an arbitrary reduct, I don't see why this notion should behave well. Okay, and the last thing is to show that this notion behaves well in this particular reduct. And so this is the theorem we're going to. So let me just take the third. So how long I have left?
A few minutes.
Yes.
5 minutes.
So let me just say the third ingredient, which is the important ingredient from number theory, but I'm not going to explain what it is. It's the actionual theorem. And in some sense, the whole idea of the project is to reduce Liouville theorem to actionual theorem. Okay, and it's not a surprising fact in the sense that, for example, I mentioned the Risch algorithm, okay, in the 1970. Actually, in the paper, so in the acknowledgement section of the paper, is just taking James Axe, right? So, and the paper is in 70, the paper of Axe about the actionual theorem is in 71. So from the beginning, the actionual theorem is very related to the problem of integration in finite terms, and this is what we use to express that this reduct here is not a random reduct of DCF. It's something that has very strong algebraic properties that comes from here.
What is the middle row? F equals C?
C, then you get the pair of algebraic
What
equals
is C?
the field of constant.
You can see again.
Ah,
The currency.
okay.
So I'm confused. Yeah. So it depends if you, yeah. So the main theorem that makes the whole thing work, let me explain it. And then I'll stop here. So which explains the model-theoretic setup, and there are other situations when we hope that there is a similar model-theoretic setup, is that consider the reduct associated with f equals gamma. Okay, that I've given previously. Okay, and red is a map which goes from C CF0 to the reduct. And so the following are equivalent. And the first one, so you're given, so let P be a type, okay, which is weakly orthogonal, which is weakly C orthogonal. Okay, then the following are equivalent. So the first one is that P has a faithful reduction. This P has a faithful reduction. Okay. The second property, okay, so you see this is a property of P here. The second property is that actually the image is finite dimensional. So has finite model rank. Okay, so you see what is funny is that this has nothing to do with the reduct anymore. It's only a property of the theory here. Okay, so these two properties are equivalent, and this is what gives this definition some good properties. Okay, and the third part is the part that allows us to compute for the problem of integration in finite terms, is that this is equivalent to say that P is realized by an holomorphic function okay, they are definable in R. Okay, so we can completely forget about the notion of definability in a minimal structure, and we have a completely algebraic system which takes a differentially closed field and produce a reduct Okay? You have this map that you get at the level of types. Okay? This is a completely algebraic framework. And to ask a question, is this function locally definable in this structure, is equivalent to know either if the image of your type is finite rank, or if your type has faithful reduction. Okay, and using these three properties, we are able to do what we usually do in omega stable series, but to apply it to the reduct and get a result about the problem of integration in finite terms like that. And I will stop here.
Questions or comments? To also get something about computational ability or computability.
So we think that this should also give some nice clues about things that were wrongly done, I mean, that can be improved in the computational aspect, but we don't know enough about, I mean, the theorem of Rich is very long and very difficult, and so we haven't had enough time to look at it and to see that it can improve this. We hope it can, but we have no concrete evidence that it's actually a better way of thinking about it. But when you look at I mean, there's many things that so the literature on the problem of integration in finite terms is enormous, and there's many times then where we realize that in our framework it's better to do something, and then we go see at the classical literature, and then we see that, indeed, Liouville already knew that this is more convenient to do things like that. So yeah, so for the moment we hope it can help a little bit, but yeah, but we have mainly tried to think on the geometric aspect. What are the functions that are exponentially algebraic and not elementary, and where these functions appear in the differential calculus, like the Lambda function, like using elliptic integral and making change of variables and getting problems from classical mechanics, so this kind of things, but we don't know if it helps on the computational side.
More questions? One more occasion. Maybe let's thank the speaker again.